All right. And so, yeah, and you can also see my share screen.
Yes, I can.
Okay, perfect. All right, good. So for this week, module 3, it will get a little bit more technical. Okay, that's when you will study a little bit harder in order to get the hang of it, because it will involve calculation. Calculus. Involve differentiation and integration in the calculation of the probability. So it is not that straightforward, and you need to recall your calculus a little bit if you have graduated from the school with that course taught a long time ago. Go back and refresh it a little bit. All right. So here, let's take a look at the topic 3, and we see random variables and moment generating function. MGF stands for moment generating function. First, what are random variables? Random variables are numbers that can are variable that can take on any number within a specific range according to certain probability, okay, or randomly, okay. Random, if for example, from 0 to 10, from 0 to 6, no, from 1 to 6, for example, suppose you toss a die, and the number you will end up have is either 1, 2, 3, 4, or 5, or 6. But each number, the probability for you to land on each number is according to a probability, which in this case, if it's a fair die, it will be 1 over 6, about 16.7% probability for you to land on a specific number, 1 to 6. That is random variable. And there are random variables that can take on only discrete values. There are random variables that can take on continuous variables, okay, in the entire real line, And so this is the concept of random variables. And for example, if it's a normal distribution, then it will be able to take on values in the entire real line, including negative and 0, not just positive, according to a bell-shaped distribution probability. The shape, the height, the height that correspond to a certain specific value in a certain point of the real line is the probability. And so if you connect the height of all the probabilities of every single value, you will get a continuous probability distribution. Okay, so that is a general overview of the random variable. And what is moment generating function? Moment generating function is used to generate the first moment, second moment, third moment. And first moment is mean, average. And then what? And then use the rest of the moment generating functions. You can generate the statistics with respect to that specific random variable. Okay, that include kurtosis, that include skewness, and so forth. So moment generating function is valuable characteristic and important function. Okay, but require a little bit for you to digest. Okay, So stay with me. And we will cover these chapters. Basically, actually, I only have assignment for 5 and 6, 2.5 and 2.6. Yeah. So focus on 5 and 6 on random variable and the moment generating functions. Now, let's go over to the course materials. Click on the chapter 2 probability theory. You will have the course material here. Let me see if I can. 1 second. Okay, let me open it in oh, sorry. Where is that? I don't know. Okay. Anyway. Okay. I'll just open it here. Oh, okay. Now it's better. Okay. So you have this. I'll scroll down to section 2.5. Okay, I'll quickly go over the examples. For example, as I mentioned, let's look at this example as I'll use examples as part of the lecture because an example is easier to digest than theory, too theoretical. Now here, so if you toss the 3 fair coins, then what are the possible outcomes? They are 2 by 2 by 2, 8 outcomes, because each coin has 2 outcomes, head or tail, head or tail, head or tail. But then each outcome, the total number of outcome is 2 by 2 by 2. Okay, so that's 8. But there's only one case, which is what? 3 heads or 0 tails. X is number of tails. Okay, so 3 heads, that means no tail. X equal to 0. So X, this random variable X, stand for number of tails out of the experiment of 3 coins tossed at once. So you have X equal to 0, probability is 1/8. X equal to 1 is HST or TH or THH. So there are 3 of them out of 8, and so forth. So you can build a table with value and probability. As I mentioned earlier, the random variable will be the value of the random variable can be chosen according to a certain probability, and this is an example. You have 0, 1, 2, 3. All these, you can only have these 4 numbers, 0, 1, 2, 3. But each one appear at different probability, according to a different probability. So this is what discrete probability, discrete random variable. Okay, and actually this follows a binomial probability distribution, but I use it as an example to illustrate it. Okay, so probability X equal to 1 is 1/8. Probability of x equal to 2, equal to 0 is 1/8. Equal to 1 is 3/8. Equal to 2 is 3/8. Equal to 3 is 1/8. Okay. All right. Now, now you will say, oh, what's the probability that if we toss a fair coin twice, then there's 2 by 2. There are 4 possible outcomes here in this S, in the sample space S, which is H, T, T. So with that, then we can count how many. Suppose X is the number of heads. Now X become heads. So can you have 0 head? Yes. 0 head is TT. There's only 1 out of 4. 1 head include HT or TH. So 2 out of 4, that's half, 50%. And probability of 2 is 1/4. Okay, so with this, then you can calculate what is the probability that you have the number of heads that's less than or equal to 1.5. Then, of course, there's no 1.5 heads. There's no such a possibility, but so you can only have what? 0 head or 1 head. But the probability of 0 head or 1 head is a quarter plus a half. That's 3/4. 3/4. Okay, and this 2.5 is a cumulative probability, and so you can see when it's less than 0, you have no probability. And then from 0 to 1, the probability is 1/4. The height is 1/4, and because it's cumulative, so you keep going up higher and stop there. This is a 1. The height of the here is 1. Is 1. Okay, 1/4, 3/4, 1. Okay, so this is cumulative probability. That is discrete probability. And discrete, you see there's gap between it jump from one value to another. Okay, it's not continuous because you don't have 1.1 head, 1.2 heads. You only have 1 head or 2 heads or 0 head or 3 heads. Okay, depending on how many coins you toss. Now, and when it's come to the continuous random variable, we use what? Integration instead of the summation. Summation, you see, this is a summation of all previous probabilities. And so, you know, if you recall the way calculus is for, calculus is to divide a certain area into many slides, very, very small pieces of rectangles. And when you sum up those pieces of rectangles, you can approximate a probability under that irregular shape accurately, and that's a calculus and integration. I mean, specifically. So because there is no gap, but actually, if you look at it this way, you might use a microscope, use a microscopic view. You will still see, even though they are continuous, you may say that they are made of infinitesimally thin rectangles, and with that you can construct a continuous distribution. That's what the calculus, I mean integration, come into play. Okay, so if you are to calculate the area within a certain interval, like P A less than X less than B, the probability of that, then you calculate the area under the curve with the function. Okay, so here's Okay, so for example, this is x data can go from any value between the real line in the real line, but this curve follows a certain function. So in order to calculate this central area, shaded area, you will have to use calculus because we don't have a formula for such a shape. And for calculating such a shape, you have to use calculus. First, you calculate actually you use this formula. All right. This is a formula to calculate the shape under the curve, which is ft, and range goes between a and b. Okay, so and then, or you can write in another form, which is fb minus fa. Fb is cumulative probability up to this point of b, which is all the areas to the left under the curve, to the left of b under the curve. Then fa is a probability, cumulative probability from the very beginning, very last point, which is actually is negative infinity. We don't know exactly when it starts. It starts from negative infinity. So from that point on up to a, and the area is fa. So if you do fb minus fa, you will get the probability within this interval. Okay. Okay. So now let's look at the specific function. This function of probability, given this function, and what is you'll find lambda. If it is the probability, if it were to be a PDF function, then what must be satisfied? This must be satisfied. Here you say we need this integration to be 1. Because otherwise it's not called a PDF function. A PDF function is a probability density function, PDF, probability density function. Okay, and so if you draw it, it will look like that because it's altogether positive. Even with the x is positive, so this function can only be positive, and its range go from 0 to positive infinity. Is on the positive real line. And so to calculate any area, first of all, this area under this curve between the horizontal line and this curve must be equal to 1. Must be equal to 1. That's how you can calculate lambda. Okay, so you apply this rule here, right here. Okay, we replace that fx by lambda x times e to a negative x. Okay, so with that, you have e equal to, from negative infinity to positive infinity. We set up the formula first, but then the lower bound starts from 0. So you replace negative infinity by 0, and positive bound will still go to infinity. Okay, so and then you replace f of x by the function and then time dx. So your job is a little bit challenging for you, is that you have to do the integration. This is partial integration by parts. Okay, if you still remember, integration by part. I won't have time to do this for you. You have to go over it, review it, or search internet for it. It's not hard, and there is actually a calculator which could do the integration for you. All right, using integration by parts, you will be able to get lambda and end up lambda equal to 1. Once you get the function to this definition for PDF, you can then come back and integrate the cumulative area to the left of any specific x value. All right, so here is a formula. You have to now that lambda is 1, So f of x is x times e to the negative x. And here we replace the x by t because we use dt instead of dx, then it will be like that. And you integrate it by part again. By part again is like that. So, and if you plot it this cumulative distribution function, it will be that. All right. So this is a random variable, and for this one, the function is linear. Okay, linear. This is non-linear. So with this function, you what? You will do the same thing, right? Similar thing to use that formula for cumulative probability distribution, and to calculate all these. Okay, to calculate all these, right? All this, and then you will get the probability. So you will refer to this example. And now, if we look at some of the questions in 2.5, 2.5, 4, 9, and 12. Okay, those are the ones we will look at. 1 second, where is 5, 4, 9, 12. 4 is this. Okay, so calculate probability x equal to 2. So what is that? That's very obvious. This is easy. 0.4, right? 2. The probability correspond to 2 is 0.4. And x greater than 0 is what? What are greater than 0? 0, 2, 5, 6. So you take the sum. 1 second. 1.4. 1, 2. 1 second. Probably PM. Oh, okay. The PDF is for continuous, but discrete is PMF. Given in the following. There, I think that, yeah, there is a little bit there's typo for this question, because it's not supposed to be, because the sum have to be 1 and this exceed 1. So there is typo in here. There is typo. It cannot be 1 because look at this one is correct. 0.2.1.4.3 2143 is 1. Okay. 1 second. This one is incorrect, so I will change a question for you to work on. Maybe 5.252. 252, because that question has 252. Let me change this to 252 for you, because 252, because that one, that question has mistake. Let me change it right now before I forget. And so forget about 2. Let me change it. Yeah, we don't do 2.5.4. Let's do that one. It's wrong. So let's do 2. Excuse me. Okay, so let's do 2, 5, 2, 9, and 12. And so what are the 9? The 9. 1 second. 259. I'm going there. 259. Okay, 259. Yeah. All right. So to find the probability density function, you will do what? You know, how do you get the cumulative distribution function, capital F of x, is through the integration of the density function. So now that you get the density function, I mean cumulative probability function, in order to get a PDF in a reverse way, what should you do? You should use differentiation. Instead of using integration, you have to use differentiation, because through integration, PDF become what? Become a CDF. All right. So now, if given CDF, how do you get PDF? Through differentiation. So you will differentiate this with respect to x, and so this will excuse me, this will test your calculus a little bit. All right, I will leave this to you as well. You should be able to find this type of integration and differentiation. You see, this is a formula. So the capital F of y is the CDF, but then small f of t is what? PDF. So since you integrate it to get capital Fy, how do you get the small f ft, which is PDF, to differentiation? Sorry. Okay. Okay, so that's 2.5.9 and 12. Again, A, as mentioned in the example, the value alpha, the PDF function is given right here, but there is a unknown constant here. So, excuse me. How do you get the calculate this alpha? You will integrate this based on the range of x and set it to 1. Set it to 1 to get alpha. And then after you get a PDF, after you calculated the alpha, you'll get the PDF, and then you can calculate the value excuse me, within this range, which is desired area as the desired probability within this interval under the curve, under this function, okay, with the alpha calculated under A. Okay, why? Because we saw this this formula, right? This formula, we need to all the area under the curve had to be 1 if that has to be if that has to be a PDF function. Okay. All right, so that should be clear. So I will leave the calculation job to you because we have moment generating function to handle right now. Okay, moment generating functions, as mentioned, is it says one of the most useful concepts in probability theory. Okay, And the expected value may be viewed as the balance point of distribution of probability on the real line, or in common language, the average. Okay, and here you see that in order to calculate probability, you just take the sum of all the products of value with its probability. Okay, if in the table in previous, for example, take this example 262. How do you get the expected value? Just take the sum of the products. -1 times 1/7 plus 0 times 1/7 plus 1 or times 1/14 and so forth. The sum of the products of the random variable with its related probability will give you the mean, the average. Okay, and so this is obvious. Then let's see. Okay, 2.6.4. We see that there are n different values, n different values, 0 to 0, 1, 2 to n, so n plus 1 actually, n plus 1 values. And so for that, you have so many, but each value has equal probability, which is what? 1/n. 1/n. So let me see. X is could be less than the rest. Let me see. X1, X2, and oh yeah, the probability is altogether the same. The same. The same. And what are the values? Excuse me. Oh, we'll skip this one. This is not a big deal. Okay. Now, what's a variance? Variance is the expected value or the average of the difference of that value from center square, the expected value of the square of the deviations That's a variance. Okay, this is the formula. I think I've shown you before that population variance and formula is different from sample variance formula. Okay. Anyway, and you can calculate the mean and the variance of a specific variable, and you can also calculate the expectation of function of a random variable. You see, instead of calculating the mean x, we calculate the expected value of function of x, which is g of x. G of x. So if x is discrete, we use summation. If x is continuous, we use integration. And these are the properties of expected value and variance. Value and variance. Okay. So if the expected value of constant c is just itself, because there's no random variable involved. And if you multiply it by a c, then every expected value will be multiplied by that c. So it just pluck that out of the expected value will be it. And so on and so forth. But when you come to variance of ax plus b, you have to be a little bit careful. Ax plus b is a constant, so ax probably the variance of ax plus b is actually the variance of x. but the variance of AX, the multiplication of A to X changes its variance to the scale of A squared, not just A. You don't just plug it out and multiply it by A like you did it for the mean. You have to multiply by A squared. Why? Because the formula here is what? It's squared. It's squared. Okay? It's squared. So when you take that constant A multiplied by X out of that formula, you have to square it. Square it. And also the variance of X equal to the expected value of X squared minus the mu squared. And that can be proved by here. I'll skip that part. Okay. So with that, you should be able to calculate the expected value of X. It's just omitted the bracket, okay, left and right bracket, and just write EX, but that means expected value of X. All right. And as mentioned before, to find out expected value of something is what? Is just to is just to find the sum of the product of the value and its associated probability. So with that, but every value has equal what? Probability 1 over n. And because it's uniformly distributed, if you draw plot its figure, it will be bars equal of the same height, 0, 1, 2, 3, 4, 5, and so forth. And the height is 1 over n, and the value is 1, 2, 3, 4 to n. Now you can calculate the expected value of X squared, which is like that. Okay, and you have to use a summation formula, which you learn probably in high school or in college. Okay, and apply it to here. Okay, now once you calculate, excuse me, the expected value of X squared and the square of the expected value of X, which is mu, right? Which is this formula, you know. Expected value of right here. The mu is what? Expected value of X. Okay, mu is expected value of X. So hope you won't be confused. This one is expected value of X squared. All right, and this is the square of expected value of X. This is different. All right. So you use the result in here, you will find the variance. All right, not very straightforward and not very and a little bit confusing. So, all right, no, I think it's notation part, and so you will get used to it by studying it a few times over and over. Okay. Okay, so these are the same thing. I won't repeat it again. So you will do it. Now, let me see. I will cover one more, and I will cover the questions. 1 second. Here. 1 second. 1 second. Let me show it. Here's a moment generating function. Moment generating function of random variable x is to what? The moment generating function of a specific value of x is to find its expected value of what? E to the power of tx. So okay. to find the mean of x is e of x. But to find its moment generating function is to find the expected value of e to the power of t times x of that random variable. You raise the random variable to the power of e while multiplied by x, by t. Okay, so this is what we call moment generating function. And also, there are two forms, discrete and continuous. All right. Now, you can develop it in this way, according to the Maclaurin series of the function e of tx, which you learn in calculus. And then you have moment generating function is written by this function, or okay, because e to a expected value e to a power of tx equal to e expected value of what is Maclaurin series. And then but we learn that the expected value of 1 is 1, expected value of tx, so the expected value of this thing equal to expected value of each individual item. And so if you take the differentiation with respect to t of every single item, you will get this thing for we call it the first moment. Now, if you set t equal to 0, what will happen on the right hand side is that because all the second term or higher will be 0 because all are multiplied by t. So all the second, third, or higher term are gone, and only the first term is left. So the first moment generation function, when setting t equal to 0, you will get its mean. And if you do the second derivative, okay, you will what? And then set t equal to 0, you will get expected value of x squared. And you do this for the third and for the fourth to the nth derivatives, you will get this formula. And you generalize it in this way. Okay. So what does that mean to you? That means you can use a general, that give you an alternative in calculating the first moment, second moment, and to the nth moment. And then by setting t equal to 0, you can get the mean, you can get the expected value of x squared, you can get the expected value of x to the power of 3 to the power of n, and so forth. Then come back with that, you can calculate your variance or your skewness, depending on how high the moment you want to cover. Okay, this is a little bit challenging, I know, but so I didn't give you too many questions on this. But these examples you will have to refer to carefully when you work on your homework. Okay, let me see. Let me get yeah, maybe I show you this example. For example, I give you this PDF function, all right? PDF function, and find a moment generating function. So we know the moment generating function is expected value of what? E to the power of tx. Okay, so instead of integrating it with respect to x to find its mean, we integrate e to the power of tx times its PDF function to find its moment generating function. So you have to plug this whole thing into the formula and work out the integration, and this is the form you get. But then what can you use after you get this moment generating function? You can differentiate it with respect to t once, set it to 0. You can get this mean. the mean for the random variable x. And then you can differentiate it twice and set the t to 0, you'll get the expected value of x squared, so on and so forth. Okay, so I think and so forth with the other examples. I will probably leave the other examples for you to study. Okay, and let me see the questions I gave you. 3, 6, and 8. Excuse me. So 3, 6, and 8. So here you see how do you get 3 is easy. Okay, you can do it yourself. For example, to find E expected value of y squared, you just take square all the y value and multiply by it. First you have to calculate the PMF. This is a cumulative mass function here. So you have to create right under this another row, which is what? PY, which is a probability mass function. So it should be 0.1, 0.05, and what? 0.25, and what? 0.4, and then 0.2, right? You turn it into PDF, and then multiply the square of it to that PMF, respectively, right? You will get it. And how do you find its moment generating function of y? Moment generating function, you have to go back to the formula. You will see the moment generating function is right here. So you will do what? E to the ty. What's the question number? 26. Oh, yeah, right here. Sorry, right here. Okay, so you will do e to the negative t, because y is negative 1 times t, negative t, e to a negative t times 0.1 plus e to the 0t, so it's 1. 1 times what? 0.05, because, you know, and then you calculate it for the first question. And then plus e to the 2t times 0.25, so on. And then you will get the moment generating function of y, so on. So, and let me see, 6 is kx squared. So you can refer kx squared, you can refer to like 2610 example, 2610 example. Okay, 2.6.10. Okay, and 2610, and then 2.6.8 is okay. This is also not difficult. Find expected value. So you will use the formula, the properties in use the properties here. Right here. Where? Right here, 262. Okay, theorem 262 in page 94. Okay, I think this is a good point to stop. Is almost 1 hour. I know it's much harder than previous lectures, and yeah, very good. The first 2 weeks is just warming you up, and This is the beef of the class. Okay. Very good. Any questions?
No, not right now, Professor. If there are any, then I'll let you know.
Yeah. I know you have to work on it before you know where you get stuck with.
Yep.
Yeah. Right. So whenever you feel like you are stuck, two ways to move on. You can search for like partial differentiation, partial integration. Okay. Then you know we have differentiation and integration problems, and then refers to the examples and theorems that I have referred to. I will add more hints and tips on the assignments. Okay. And then also you can watch this lecture recording again. So all these will help, and then otherwise you post your question and I will do my best to help you. Okay.
Okay, Professor. So I have a question. The discussion is not open yet. I think it's going to open on Tuesdays, right?
Oh, yeah. Sorry. You know, I set all the days a week before class started, and so there might be. I will do it. I will correct it right now. Okay.
Okay.
Yeah. If not now, maybe wait for like 20 minutes. I will make the within an hour also, because the recording of this video is quite long, and so it will take a little bit before I post everything online. Okay. Yeah, I will correct that as soon as I can, immediately. Okay. All right. Good.
Okay, Professor. Yep. Thank you.
Okay. Good. All right. Good. I wish you have a very good evening. Okay, and have a very good week studying this interesting material. And although it's challenging, you will feel a sense of accomplishment when you get everything done. All right.
All right. Thanks.
Okay. Good. Have a good evening and see you next time. Okay.
Yeah. Bye-bye.
Bye.